Hello, my name is Maxat Kulmanov, and I'm a research scientist at Bio-Ontology Research Group at King Abdullah University of Science and Technology in Saudi Arabia. Today, I would like to present our recent work called DeepGOZero, which improves protein function prediction from sequence and makes zero-shot predictions based on ontology axioms. So, by predicting protein functions, we mean predicting gene ontology classes. Gene ontology provides a vocabulary for describing proteins and their functions. It consists of three parts. The first part is biological process ontology, which describes the processes to which a protein can contribute. The second is molecular function ontology, which describes a biochemical activity of a protein, or a cellular component ontology, which describes the cellular locations where a protein can be active. So gene ontology has more than 50,000 classes, and it has very rich knowledge in terms of axioms, in terms of thousands of axioms that describe these classes and their relations. So there are many methods for predicting protein functions, from protein sequences, structures, secondary structures, or protein-protein interactions from literature, or their combinations. But our main focus and our main research question was about how to incorporate this knowledge in Go into protein function prediction model to improve it. So the first method that we have developed previously was called DeepCO. So DeepCO predicted protein functions from protein sequence and interaction information using one-dimensional convolutional neural networks and sequence embeddings. And it encoded the hierarchical structure of Go directly into the neural network in the form of linear layers that were connected with each other in the form of gene ontology structure. So it was one of the first methods that used deep learning also in order to predict protein functions, but it had some limitations. It could predict only limited number of functions. It was a bit slow to predict and train, and it had not the best performance. So then we tried to focus on runtime and prediction performance, and we developed DeepGO Plus. Here, we had to remove this hierarchical structure of the neural network, which encoded Go, to gain more runtime. And we combined our convolutional neural network predictions with sequence similarity methods. And it overcame some of the limitations of DeepGO. However, the knowledge in the ontology was only used post-prediction. So after running the model, we used the ontology structure to fix the hierarchical dependencies of the predictions. Also, we encoded the gene ontology structure, the information and gene ontology structure directly into embedding space in our method called EL embeddings. Here, EL embeddings uses the axioms and directly learns from them on how to embed the ontology structures and ontology classes into RN so that the embeddings would preserve the semantics in the ontology. So we applied this model into proteins interaction prediction and showed that it can improve the performance for this task. In EL embeddings, we normalized the ontology axioms into 4 different normal forms and generated some of the negatives as well, and encoded, for example, the disjointness using the second normal form here. So here, EL embeddings represented an ontology class as an n-ball with a center point as a vector in Rn and a radius, a scalar value for a radius. So this way, we could represent a class which could encode for many of the instances that lie inside. And for example, if one class is a subclass of is another class in the ontology, in the embedding space, the n-ball of the class would lie inside of its superclass. So we modeled the relations also using trans-E relational model, where we add and translate, for example, if there is exists some relation D, we add an embedding for this relation and then translate the n-ball to a relation space. The intersections of classes, so if intersection of 2 classes is a subclass of another class, so we make sure that the area that intersect of the intersection of 2 classes lie inside of the class in the subclass. So in DeepGOZero, we embed the proteins also in this embedding space that is learned by EL embeddings. And then we optimize this process jointly. So a protein is embedded using a neural network into Rn. So we learn a representation for this protein, and we assert the axioms that protein is a subclass of has function SUMGO if this protein has been annotated to this DeepCO class. So for example, here, this protein will also it will also learn that this protein is related to some of the other Go classes, because there are axioms in Go, like if this protein has this function, the axioms also will learn that this function is a subclass of positive regulation of another class, and that class also will be related to this protein, even if it's not, even if it doesn't have any annotations to it. So the prediction score of a class for a protein C is computed using this function here, where we have an embedding of a protein which is generated by a neural network, and embedding of has function relation, embedding of class C and its radius. So we use the translation of the embedding of the class. Then we get the dot product and add the radius to it. So this radius represents, in some way, it represents the generality of the or specificity of the class. For specific classes, we have very small radiuses, and for general classes, the radius is larger. We then optimize our training data, which is our annotations, where we have P has function some class, together with all the other normal form losses that we optimize. We optimize this loss jointly. So for our data sets, we use two data sets where we have our own data, which is a UniProt SwissProt release in November 2021. And we use 50% identity similarity. We do this because SwissProt database has many sequences that are identical or that have more than 70 or 90% similarity, and they share very similar functions. So if we use these sequences in our training and testing set, we end up having almost duplicates in our training and testing sets. And the models that are learned using these data sets, that if we split randomly, they will get overfit. So to avoid this, we use 50% identity. So it makes sure that no sequence has more than 50% identity in testing set or validation set. And then we split it into 81% training, 9% validation, and 10% testing. We then also take another data set to compare with other methods, a data set generated by DeepGO 2, which is a time-based split and which follows kappa rules to generate the data set. We compare with our own baseline methods that we evaluate on our data. We use diamond score, sequence similarity based predictions. MLP is a multi-layer neural network, DeepGO CNN, and DeepGO Plus. We also compare with other baseline methods. We have DeepGO 2, which is an ensemble method. It combines many different features like protein sequence, protein-protein interactions. We also compare it with DeepGRAPH-GO, which is a graph convolutional neural network based model. And we also compare with Tail Plus, which is transformer based neural network prediction combined with sequence similarity. So on our data, our method shows that it can achieve best performance in terms of term-centric AUC. So here we are using 4 measures. The first 3 are protein-centric, so it means that we average by proteins. And the last one, AUC, is term-centric. And our method shows that it can achieve the almost similar performance with simple MLP network combined with sequence similarity. And it gets 0.668. And it achieves the best in terms of term-centric AUC. That is also true for all 3 ontologies. For time-based split, we see that DeepGOZero achieves the also very good performance in terms of term-centric AUC for molecular function ontology, but however, in terms of Fmax and Smin, it cannot outperform, for example, DeepGO. So here we use DeepGRAPH-GO and Tail Plus trained models and evaluate and then run them on our testing set. And DeepGO 2 method was we used the web server for netco2 method in order to obtain the predictions for the test set. So we see that netco2 has like Fmax of almost 0.7, but here we are not sure that if our testing proteins, although we use the same their data, we are not sure if they use them in the web server as a training. And DeepGRAPH-Go achieves the best Fmax in terms of CCO ontology. However, our MLP method shows the best performance for biological process. So since DeepGOZero achieves the best performance in terms of term-centric AUC, we decided to look at the specific term predictions. And when we compare the predictions for the specific terms, which have the annotations from 1 to 100, we see that for those functions with annotations less than 50, DeepGOZero achieves the better performance than MLP. Although in terms of Fmax, it's not very good. So this shows that DeepGOZero improves predictions for specific terms. That is the reason it has better performance in terms of term-centric AUC. We also can make zero-shot predictions because since we have embeddings for all the 50,000 classes in the ontology, we can generate predictions. And for those classes with definitions, we can even get better performance because they have more knowledge and more relations with other classes that have some training proteins. To test this, we took all the specific classes with less than 100 annotations. We removed them from our training set, and then we generated zero-shot predictions. We see that we can get an average for our testing set, we can get a performance of AUC of 0.74, and for all data we get 0.8. Of course, if we evaluate the trained models on this data, the performance is better because it was supervised in a supervised way. It was trained with those predictions. We also compare like all the classes and then defined classes. So the classes which have some axiomatic definitions, they get better performance in average. So in summary, DeepGOZero achieves best performance in class-centric evaluation, and it improves predictions for specific classes, which is important because we are more interested in predicting specific Go class annotations. And it also can make zero-shot predictions for those classes without any of the annotations, just using the knowledge in Go. So the current limitations of DeepGOZero is that it only uses interprogramming annotations, and it also uses EL embedding loss functions, which have some limitations because it cannot model many-to-many relations. And we did not use all of the types of axioms, so we did not use the all knowledge in the ontology. So in future, we would like to incorporate these more sequence features, interactions, or structure into our model. And there are also some methods that already overcome this class intersection limitations of EL embeddings and can model this class intersection better than EL embeddings. So we would like to test them as well. And with that, I would like to end my talk and thank you all for your attention. If you have any questions, feel free to ask.